Let's look at reactions of specific orders. We'll start with first order reactions. An example of these types of reactions are radioactive decay, are all first order. And we have some reactant going to a product. And we know that for first order, the rate expression is equal to the rate constant K times the concentration of the reactant raised to the first power. So that's first order reaction. So we have two equations for the rate of the reaction. This is one. The other equation that we can use is this, where we look at the change in the concentration with respect to time. So now we have these two equations for the rate, and so we can set them equal to each other. And so I'll set them equal. Now this is just a first order differential equation, it's ordinary, constant coefficient, so it's easy to solve. We can actually just solve this by integration. But you won't have to do that in this class. I'm going to show you the solution and how we get the integrated rate expression, but you don't have to reproduce it. So I'll get all the A's on one side of the equation. Then I have the A's on one side and the T's on the other. So this is called separating variables. I have the A's on one side, the T on the other. So now I can integrate this expression, and if I simply integrate, I'll integrate from 0 to T. So I'm starting at time equals 0, going to time T, and at time equals 0, I'll say the amount of my reactant is an initial amount. So I use this 0 here to stand for time equals 0. So this is the initial amount of A. And at time T, I'll have some concentration of A reactant. So I can do this integral, and I will get on the left the natural log of A evaluated from initial concentration of A to A, and then on the right I'll have minus KT evaluated from 0 to T. So putting in my integration limits, I'll have the following expression, and I'll combine the logarithm terms into a quotient. So this is called the integrated rate expression. So it gives us the concentration of A as a function of time. So this is analogous to a trajectory in classical mechanics. So now if I know the concentration of A, the rate constant, initial concentration, I can find the time. Or if I know the time and the initial concentration in K, I can find out what the concentration of my reactant will be at that specific time. Another form of this equation that is useful is I'll take the antilog of both sides, and then just solve for the concentration of A. So this is another useful form of the same equation. So here I can solve for T easily, but here I can solve for the reactant amount easily. So you want to be familiar with both forms of the equation and how to get from here to here and vice versa, and be able to just use this equation to solve for concentrations and times.